My name is Dr. Shobhusha Chishen. I am the Dean Research and Development of JIS College of Engineering. But herein I am here to talk about my physics courses. Okay, I am basically a physics teacher. I do take physics in the classes in the BTech courses, so first and second year. So now here I am talking about my second year courses, which is called Physics 2 courses. Now, second year course in Physics 2 is separate for separate branches. For computer science and IT, bokeh is something. For mechanical, civil, it is different. For electrical, electronics, all are different. Obviously, they are learning in a different semester. Now, it is stream specific. It is as per the requirement of your own subject. Okay. Say in the computer science and IT syllabus, we have added the latest computation like quantum computation. Like the applications of latest materials called nanomaterials, how the storage and display devices works. These things are not so much connected with the mechanical and civil engineering, who are also learning physics 2 in this course. So we have kept courses like the ultrasonics, okay, which is applied in mechanical and civil. The concept of building acoustics for civil, which is not needed for you. So basically, we have made it stream specific. We made a thorough analysis of the requirement of your course from your department, from your alumni, from the existing student. We made a survey. Based on that, course objective and outcome was framed, and let me present the same now. Now the course objective of this Physics 2 course for CSE and IT student is to introduce topics, okay, is to apply quantum mechanics for learning the latest of computation called quantum computation, learn quantum logic gates. Is to, as a student, you get comprehend about the hardware sectors of your devices, okay, the storage, display part, and also the latest storage devices. The entire electronics is moving very fast, and that is because of the revolution in semiconductors and now the nano devices. Okay, so an introduction to that. So that will be another objective of this course. And also this entire communication system, okay, it's based on the electromagnetic theory. Okay, so we'll also provide you some glimpses of electromagnetic theory, because later on you have got courses on the analog communication and digital communication. Okay. Now the major course outcome of this Physics 2 course for CSE or IT student is that after undergoing this course, you will be able to explain the electromagnetic theory with your basic knowledge of electrostatics, magnetostatics and electromagnetic theory. You will be able to explain the most modern computing devices using the latest idea of quantum mechanics and quantum mechanics principle. You will be able to explain the operation of the most modern storage devices, how it evolved from the magnetic storage to semiconductor devices. You will be able to judge the requirement of the latest material for the purpose of computing, for the circuit design, and for the storage material, that is the ideas of nanomaterials. Okay, so let us, and this is closely connected with your own program, so you can get that in the course outcome, program outcome mapping also. On the screen you can see the various modules that are present in this course, and you can also see the module that you will be starting with. We'll start with one of the promising modules of the course, as well as you can also see the topic that we will begin with. And in this particular class, whatever we will be focusing on, the related prerequisite, what is the objective of the class, and if at the end of the class you're supposed to get something from me, that is the outcome of the session. So that session outcome also you can see on the screen. Hello and welcome to class 8 of my series of class on Physics 2. And we have already started our journey with quantum mechanics 2, and I have been telling you it is one of the basic need of anything you do in modern physics sector. Okay, it may be the area of quantum computation, or it may be the application of the latest semiconductor device, or maybe the latest of the electronics called nanoelectronics. Everywhere you have to utilize the ideas of quantum mechanics 2. Okay, ABCDs of quantum mechanics 2 are necessary for anything you do in some other part of your course. Okay, so that's why we have taken up this as our starting point. And just to remind you what you do in quantum mechanics courses, it's a very special area. Okay, in a quantum mechanics course we talk about only microscopic object. This is me, you can see.
and our focus is very specific. I told you that this world is a world of matter and waves. And when you talk about matter, if it is matter is on colliding, fighting with each other, then I am talking about the material property. And collision type of things, you can explain with your classical mechanics idea. And you mainly know Newtonian idea, but apart from that, some other mechanics is also available in classical physics, Lagrangian, Hamiltonian. So they are good enough to explain those mechanics of collision with matter. Now, wave theory can be explained. Corresponding sound wave theory, light wave theory, pertinent theories are there. You'll be learning Maxwellian theory in this semester also in my classes itself. And the particle nature of wave, that is the photonic property, I have taught you in first year days, so that you also know. Which you do not know properly, or the technique which you are learning now is the fourth aspect, that is the wavy nature of a matter. And wavy nature of a matter is not a dream. It has been realized through Davisson-Germer experiment. Electron was showing interference. And if this wave, today you know that when I talk about wave nature of electron is, it's usually it's a matter with some mass, some velocity, some momentum, it moves maybe. If it is moving and if it is colliding with another electron, so if it is colliding with another electron, that is not the purpose of this class. Our class is objected. My class goes with de Broglie, okay? That is, if the electron shows wavy nature, then my class begins. And this wavy nature of electron or is basically is the exhibition of wavy nature of electron is basically one of the has been exhibited or has been proved by Davisson-Germer experiment. And you should remember one very simple issue: wavy nature of electron does not make thing that means electron is becoming a wave. It means electron is showing the property of a wave. Electron is a matter. It has got some mass, some charge, some magnetic moment. So it's all the material properties it has got. But if it has got if it is colliding with another electron, that is the exhibition of particle nature. That you know. So I don't have to teach that. What I have to focus on is if electron shows wavy aspect, if electron do interfere, which you will see when you learn nanoelectronics. Electron will be interfering with each other, by which you can explain the action of the devices. And so therefore the wave nature of electron is very pertinent, okay? And that wave nature of electron is manifested by wave function psi. Psi is a mathematical function. Its squared modulus gives the position of the particle, and this total probability of finding the particle at a given point at a given time, and total probability is 1. In an experiment, you can calculate psi by knowing the by solving the corresponding Schrodinger equation. Schrodinger equation, this is a general form. From problem to problem, B, the potential energy term is going to change. Now, if I know psi by solving Schrodinger equation, we can actually develop entire mechanics. Okay, psi is a function of mathematics. So from psi, I can extract all these parameters of motion that you can see there. These are called dynamical variables. Now, dynamical variables are represented as operators in quantum mechanics. If you do right operation on the psi, you will get the corresponding function or corresponding dynamical variable. This is a list of dynamical variable and the corresponding operator, as you can see on the screen. For position, momentum, kinetic energy, etc., 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 all of them are. You can see the mathematical form of the operator. The job of the operator is to operate on psi. I have been using the word, you talk with psi as if psi knows everything, okay? And psi will respond. Now, response of psi is this much. That if I've got a function, so I've shown you two functions here, sine and cos, sine and e to the power function. If an operator P or T, say P stands for, is connected to the momentum, T is connected with kinetic energy. If the operator acting on the function gives you back the function multiplied with the constant, then measurement is possible. And if it is, and then you satisfy an eigenvalue equation. The constant appearing on right hand side is a measured value, and the function is called eigenfunction of that operator. This e to the power function is an eigenfunction, e to the power ikx shown there, is an eigenfunction of both t cap and p cap. You can see are satisfying eigenvalue equation in both the cases. And sine function is an eigenfunction of kinetic energy operator, not that of momentum operator. So with sine function, you cannot calculate momentum. But you see, if you can't calculate momentum, one thing becomes sure. Okay, what is that one thing? After some time, you will come to know. Okay, because with operator, some more interesting things are waiting for you. Okay. Now you please see after that, after just talking about a single measurement over a single psi, I considered many psis. Okay, all of them together are eigenfunction of the same operator O. So the idea is that if you take linear combination of all of them, that will also be the eigenfunction of the same operator. This is called superposition principle, and I told you it is used in the most modern computation, quantum computation. And after that, if you progress a bit, I can write down this equation in this way. If psi1, psi2, psi3, psi-n all are eigenfunction of the operator O, their linear combination a1, psi1, a2, psi2, s3, psi3, an, psi-n, this summation is also the eigenfunction of the same operator, where ai is a coefficient of linear expansion. Okay, you can get ai by using the orthonormality condition that is presented on the screen, the conjugate of the first function and second function. If they will be giving you 0 for two different functions, say sine cos, x sine x, x cos a, x square, a only sine, only cos, and for same function in its conjugate like sine square, cos square, you will get non-zero result. Okay, so this has been, we have utilized this idea, okay, for solution of some problem, because same function in its conjugate square is nothing but the normalization condition. We did solve two problems in my previous video lecture. If you see, you will see we have solved few problems. Now we come back to a new discussion with operator. You know, as I often tell, the concept of operator, the root of the operator lies in mathematics courses. It is a part of the higher algebra. Just like you study set theory, group theory, all these things in higher algebra, the operator concept or operator algebra is also a part of higher mathematics. Okay, so according to the prescription, just like I say, any operator is a Hermitian operator. That means operator should have real eigenvalue. So when you use in quantum mechanics for the purpose of our physics purpose, we are using some of its qualities. But in general, the idea of operator has its deep root in its mathematics. Mathematics base. So it has got a strong base in mathematics. So there are certain prescription of higher algebra related to these operators. Okay, according to the basic mathematics, okay, the operator should satisfy some algebraic relationship. Okay, what are those algebraic relationship I presented here on the screen? Any operator in quantum mechanics has to be linear operator. Linear means when it will, you see, I have given an example. An operator O is acting on psi. Okay, psi is a mixture of two functions, linear combination of two functions, psi1 and psi2. So if it is acting, you see it is separately acting on psi1 and psi2, and power of O is 1. Okay, so it's a linear operation. It is Hermitian operation. Hermitian operator, I told you, its eigenvalue will be real. They obey associative and distributive law. What is associative law means? If you I'll show you separately. And distributive law, you can see if you have got psi as a linear combination of two functions, psi1 and psi2. If O acts on that, it will be distributed on them separately. Okay, I think even if I don't tell, also you'll do it. Okay, these are common sense. So we are less interested about this point 1 and 2 of the operator algebra. Our main concern will be on the third one, which I have marked in red there. Okay, the commutator bracket or commutation relationship in operators. Okay, and if I understand third one, fourth one will be automatically following us. Okay, so we'll now focus on commutation relationship. You know, first I will again tell you the mathematics part of it. What does it mean mathematically, the commutation relationship? And after that I put physics into that. Okay, so what I am doing, because I am helpless, my matter is represented by mathematical function. So we are using mathematics to its best extent for the purpose of our class. Okay, so what shall I do now? I will be utilizing a first I will be talking about this third point, what is called commutation relationship. In mathematics, this is called commutator bracket. Now commutator bracket of any two operators A and B is given there. You can see there, commutator bracket of any two operators A and B is given by AB minus B. You see it is represented by this way. In a third bracket, in a square bracket, A comma B. Okay, henceforth I will only write down this much. Okay, so please keep it in mind. A comma B makes the commutator bracket of two operators A and B. A may be any two of the list of operators I have presented. So A may be T, B may be V. A may be X, B may be P. A may be H, B may be V. A may be P, B may be T. Any two of the list of operators. It is given by AB minus BA. Anybody can remember. The commutator bracket of any two operators is given by AB minus BA. Now use your common sense of mathematics. You see, you are subtracting two things. Now everybody knows from basic mathematics, if you subtract two things, you will either get a 0 or you may not get a 0. Now if you get a 0, then you have got some physical meaning, some meaning, and if you don't get a 0, then you have got some other meaning. If you get a 0, then you say A and B are commuting with each other. And the physical meaning is that corresponding dynamical variables could be measured together in an experiment. And if they don't commute, And if you get non-zero, then the meaning is that corresponding dynamical variables could not be measured together. ফোন করে লাইনটাকে এটা কেটে দিচ্ছি। Okay, if I get a zero, then it has got some meaning, and if I do not get a zero, then it has got some other meaning. Okay. So if you get a zero, it has got some meaning, and if you do not get a zero, it has got some other meaning. Okay. Now, so that means if you think mathematically, it is just a very simple relationship, but it has got profound physical meaning. Okay. So what shall I do now? Okay. That if it is zero, then we say their operators are commuting, and if it is non-zero, operators are not commuting. You see, if I say like this, these are all vague words. So what shall I do now? I'll do it in front of you. I'll show you mathematically with some examples, so that what does it mean by commuting, and after that I'll put physics into that. Just like that, I'll show you, I'll solve a problem in front of you. Okay, so let us do that. Okay, then everything will be made more easy. Okay. IP webcam browser. Now here you are. Okay, let me show you. Okay, it's very interesting, very funny. You see, suppose I've got two operators A and B, so their commutator relationship is given by AB minus BA. So you may get zero, or you may not get zero. If you get zero, then you say they are commuting with each other. If you do not get zero, you say they are not commuting with each other. Now suppose they commute. What does it mean? Let me tell you the mathematical meaning of it. Mathematically, let me tell you. Suppose you see they are commuting means automatically AB is equal to BA. So it means ordering is not important. That means who shall come first, that is not important. You see, with scalars, suppose A is 5 and B is 4. This is always equal to 4 into 5. So okay, so I don't have to anybody don't have to tell you or teach you this. Okay, you understand automatically. What is the speciality of 5 and 4? These are scalars, these are numbers. So scalars always commute. Okay, they will always commute. Okay, scalars will always commute, but in quantum mechanics, I do not talk about scalars. Suppose A is X, B is del L X, and you can realize with your common sense, X del L X and del L X X, and that's not same. Here, this can differentiate X, and it has got nothing to differentiate, so these are not equal. So obviously they are not commuting. So in quantum mechanics, I do not talk about numbers. I am using operators as a mathematical functions. So they should may commute or may not commute. Now, as I told you, if they commute, then I have got good news. The corresponding variables I can measure together. Okay. So quantum mechanics tells me that if any two operators A and B, quantum mechanics tells me they may commute or may not commute. If they commute, then corresponding dynamical variables could be measured together. Suppose T and V are commuting, so you can measure kinetic energy and potential energy together. And if they don't commute, prescription is opposite. Corresponding variables could not be measured together. Corresponding dynamical variables could not be measured together. Okay, that is a simple prescription. Now I will show you this with a real calculation. I will show you the commutator bracket calculation in case of position and momentum. You will get some wonderful results now. You please see how I am doing it. Okay, see each and every line, because calculation of commutator bracket is very important for examination. Every year one commutator bracket calculation comes in examination. So you see how I am doing it. So commutator bracket of X and P, I wish to know the value, will be like this much. You see X is like A cap and P is like B cap. So it is like AB minus BA. So if I write down it, it will be like X cap P cap minus P cap X cap. X cap P cap minus P cap X cap. So what I have to do now, I can write down this in this way. XP is equal to, the operator form of X cap is X and operator form of P cap is minus H cut del L X, and here also minus H cut del L X, and X cap is X. So now this is a very important line. I just put it in a green box. You see, try to realize every time you do a commutator bracket problem, you will come. You see here I've got two differentiation operator. One of them is del L X. Here also another del L X. Now this is a very happy differentiation operator. It can operate on the function of X. But this this one is extremely unhappy. It has got nothing to differentiate. So let me make it happy. So what shall I do? On both sides of the equation, I will add a function f(x). On both sides, because it's an equation, on either side you can always add a function f(x). Now this first one is happy. It can act on the function f(x). And second one is more than happy, it can act on both x and fx. So if you look at the equation, it becomes like this much. xpfx is therefore minus h cut x del f del x minus minus plus h cut del L x of x fx. So therefore we can get it like this much. xpfx equal to minus h cut x del f del x plus h cut. You see what would happen? The first x will be differentiated. I will get fx, and then fx will be differentiated. So it will be h cut x del f del x. So what would happen? The first term and last term, if you compare these two, they are equal and opposite and will cancel each other. So we can now write down in this way. So we can now write down in this way. You see, it will become like this much. That xp fx is therefore equal to ih cut fx. Now the way I invited fx in my class, I can now ask him to go. So it would be like this much. xp is equal to h cut. Now everybody knows I is root over minus 1 and h cut is Planck constant by 2 pi. Now this will be non-zero. Non-zero means x and p don't commute. They are not commuting with each other. If they don't commute, the prescription is that in an experiment you cannot measure them together. We can't measure them together. So position and momentum cannot be measured together in an experiment, and that is nothing but the Heisenberg's uncertainty principle in position and momentum, which you have already learned earlier. So you are getting Heisenberg's uncertainty principle. This is nothing but the uncertainty principle of Heisenberg. This is uncertainty principle of Heisenberg. So you are getting it through operator method. So you can now write down it again. That therefore xp is ih cut this is non-zero. So position momentum could not be measured. This is nothing but Heisenberg's uncertainty principle, which tells us in an experiment I cannot measure together position and momentum of an object. Okay, I ask you to do at your home this much. Okay, you calculate the opposite. Result will be minus h cut, and physics will be same. Position and momentum could not be measured together in an experiment. A similar problem would be like this much. Okay, suppose I calculate the the commutator bracket of two more operators. Okay, say one of them is t, another is e. So if I try to calculate, this is like a cap, this is like b cap. So it is like AB minus BA. So if I follow the mathematics, it will be like T cap E cap is like T cap E cap minus E cap T cap. So now in the operator form, T cap will be T and E cap will be plus H cut del del T. If you see the list of operators, you will get it, okay? And this will be plus H cut del del T and T cap will be T. So this will be this much. So you see here, I have got a function. So again, same crisis. This is very happy because it can operate on t, but it has got nothing to do. So I add one function f of t on either side of the equation. So the equation would be taking like the form te ft is equal to plus h cut t del f del t plus minus minus h cut del del t of t is there, and minus minus it will be minus h cut t del f del t. So again you see first and last term will be cancelled. So we get this much te f of t is equal to minus h cut ft, and you can again see now I can remove ft by comparison. So this gives me the commutator bracket of time and energy. T cap is connected with time, E cap is connected with energy, and they don't commute. So that means in an experiment, that means at a given time, you cannot calculate the correct energy of an object. You cannot calculate the correct energy of an object. And you know, this is nothing but the Heisenberg's uncertainty principle in energy and time. This is Heisenberg's uncertainty principle in energy and time. Okay, I again ask you to do the opposite at your home. You do the opposite, okay? You do the E and T, and result will be just opposite, plus H cut, and the same physics will be there. So one last little example, that is, you see in both the cases I have got bad news waiting for me. Position and momentum did not commute. I get the Heisenberg's uncertainty relation in position and momentum. Time and energy, they do not commute. I get another uncertainty relationship of Heisenberg. So at least give one example where they do commute. So that this is this. So let me consider these two operators, x and d2 dx2. So what would be their commutator bracket? So x d2 dx2 will be equal to this much, x d2 dx2 minus d2 dx2x. Again, same crisis. I have got this line is very important. In all problem, this is coming, you can see. Again, this operator can differentiate x, but this has got nothing to differentiate. So help it. On both sides of the equation, add a function f of x. So if you add it, so it will be like, so very similar problem. Every year in examination, one commutator bracket calculation will come. So this will be d2f dx2 minus of d2 dx2. It is now acting on two function x and fx. So result of the integration would be the result of this commutator bracket will be this much, will be equal to x d2f dx2, double derivative of x is 0, minus x d2f dx2, and you can see here first term and last term will be gone. So basically the commutator bracket of x and d2 dx2 is becoming 0. At least we get one case where x and d2 dx2 are commuting with each other. Now the question is that what is the physical meaning of it? Physical meaning is that x and d2 dx2 commuting means, okay, x and d2 dx2 commuting means, okay, they are commuting, they commute with each other. It means x is connected with position and d2dxt is connected with kinetic energy. So position and kinetic energy are commuting. So that means in an experiment, you can measure both energy and position together. We can measure both position and energy together. Same thing you can do, because V potential energy is also a function of x. So potential energy and kinetic energy will also commute. So that means we can always measure both potential energy and kinetic energy could be measured together in an experiment. So many good news are there at the end. Could be measured together in an experiment. Okay, so this has been the way we can calculate commutator bracket in an in actual problem. So I tried to tell you the technique. So let me just get back to the PowerPoint. So XP, the commutator bracket I calculated. Okay. So this has been the calculation of the commutator bracket. Okay. So now our discussion is, so we end up here today. I have told you how to calculate commutator bracket of any two operator. Physics is very simple. Its commutator bracket initially is a mathematics concept, that whether numbers will always commute, function may or cannot commute. Our operators of quantum mechanics are mathematical operators. So if they commute, we have got some good news. Corresponding variables could be measured, like say potential energy and kinetic energy, positional energy. But if they don't commute, there lies the beauty, that if say kinetic energy, say position and momentum, energy and time, they don't commute, and that is nothing but Heisenberg's uncertainty principle. So Heisenberg's uncertainty principle I have told you in first year through some other way. Now we are getting it to operator method. So this we conclude today here, but our discussion with operators still is some pending. Next day we'll talk about the discussion about the average value in quantum mechanics. Thank you for the time being. Okay.